Hello, good evening, students. My name is Shashank, and we are on the second day of our 45-day crash course on chemistry, in which we are covering for the upcoming JEE exams. So, today I will be covering our second chapter, that is atomic structure. So, students, the first theory which we have learned in our first class, that was delta atomic theory. Later on, many atomic theories came upon, and they were again, then some drawbacks came, and they were changed and revolutionized from time to time. So in that aspect, this thing was developed. This chapter is based on that thing only. So the first topic is nature of electromagnetic spectra, electromagnetic radiation. So if you see around yourself, you can see things around yourself due to the presence of light. So the light enables you to see that thing. So what is the nature of light? So we will talk about this thing in this topic. So the light we see around is nothing but an electromagnetic radiation. So it consists of an electric and a magnetic field. This like this. This is the electric and the magnetic field which is present in the light. Like this one is the electric component, and this one is the magnetic component. What is this? What is the characteristics of this component? So they are perpendicular to each other. You can see here clearly that this is the electric field, means the plane on which the electric field is oscillating, and this is the plane, means the yx, you can call it as xy plane. So on xy plane the magnetic component is oscillating, and on the xz plane electric field is oscillating, while the direction of propagation of light is perpendicular to these two, means these three things are mutually perpendicular to each other: the electric field, the magnetic field component, and the direction of propagation. And this whole makes up the electromagnetic radiation, and this is how light was characterized. Now this wave have some properties. So what are these properties? So first of all, the first property we have is, it is called as wavelength. So you can see here, I've drawn picture here of a wave. So what is the wavelength? So before getting the idea of what is the wavelength, you should know what is crest, what is trough, and what is this graph. Okay, you can call it graph also, because it is oscillating with the increasing time. So here it is the graph. So it is going like this, then it is decreasing, then it is coming to a minima, then it again going to a maxima. So the maxima is called as the crest, and the minima is called as the trough. So it is not visible here, sorry for that. Okay, so this is the crest, this is trough, so I'm writing it here. So suppose this is the trough, so it is TROUGH. So this minima is called as trough. Then what is wavelength? So the wavelength is the distance between any two consecutive crest or trough. So you can call this distance as also wavelength, or this distance as also wavelength. This downward distance between two troughs can also be called as wavelength. So I can use show it here also, because it is not visible there. So like this. So suppose this is our oscillating field. So this is, suppose this is our trough. The minima is our trough, and the distance between these two troughs can also be wavelength. But these two troughs should be consecutive. So distance between two consecutive troughs is wavelength, or two consecutive crest is also wavelength. This is also termed as wavelength. Now the next thing is frequency. So what is the frequency? So frequency is 1 upon time period. So one cycle is completed when a particle moves from here to here. So it is called as one complete cycle. So it can be from here to here, from one crest to one crest, means the particle is on the same phase. So what do you mean by phase? So let me make it clear through this graph. So suppose initially the particle is here. So I'm not physically signifying it. I'm just taking a example to show you. It is not the way it happens. Okay. So suppose the particle is here. It is moving from here to here, and then again coming here. So the time which is taken by the particle to change its phase from this again to back to the same phase, it is called as time period, and the inverse of the time period is called as frequency. So the relation between the time period and frequency is one. Suppose this frequency is denoted by t, then nu is 1 upon time period. Next we will move to the amplitude. So what is amplitude? So if you see here the diagram, then you can say see here that this is the maximum displacement of the wave from its mean position. So this is the mean position, you can call it as 0. So this distance is called as amplitude. The next is speed. So what is speed? So speed will be simply the distance, the time which is means the distance it is traveled per unit time. So distance traveled per unit time. This is speed. We know the simple definition of speed by this. So in this case, we know that is, suppose we are taking this wavelength, so it will be lambda. And what is the time? So to complete one wavelength, it is t. I have told it earlier. So this what is 1 by t? We have seen earlier that 1 by t is equals to nu. So it will be equals to c is equals to nu lambda. So this is the relation given here. But this speed, the value of c is 3 into 10 to the power 8 for all electromagnetic radiation, and it is the truth, means it cannot be mischanged from place to place. So you take any electromagnetic radiation, it will travel with the same speed, whether it is X-ray, whether it is gamma ray or any other ray. So you will come to know what are these rays in the later slides. So these are the various aspects of electromagnetic radiation. So each of this will travel with a speed of 3 into 10 to the power 8 meter per second. Now, what is electromagnetic spectrum? So we know that the speed of light is fixed, that it is c is equals to nu lambda. C is equals to nu lambda. This c is fixed. So let me write it here. So we know that c is equals to nu lambda. This c, the speed of light or the speed of the electromagnetic radiation, is fixed. But this thing here, nu and lambda varies with each other. That is, nu is inversely proportional to lambda. Now, if we vary this nu, we get different lambda. And for each lambda or for each frequency, we have a different spectrum. Like this. This is the spectrum that we know. So this is the electromagnetic spectrum. So you can see here that this is the wavelength that is going on from this to this place. So this is the wavelength here. This one, 10 to the power minus 16, 10 to the power minus 14. And if you see frequency, then it is just increasing in the opposite direction. So it shows that wavelength and frequency are in inverse relation. So for 10 to the power 24, it is 10 to the power minus 16. But if we decrease this by 10 to the power 22, then it increases to 10 to the power minus 14. So we can see here from this chart also that frequency and lambda are inversely proportional. Now we divide this electromagnetic spectrum into various parts depending upon the frequency and the wavelength we consider. So the electromagnetic radiation with the maximum frequency is called as the gamma rays. Then we have the X-rays. Then we have the UV. This is our visible spectra. So what is visible spectra? So it is the light or the electromagnetic radiation which is visible to our naked eyes. So it consists of this much light. So it is the red which has the minimum frequency. Okay, and this is the purple with Bohr. So it increases like this. So this is violet. This is red. So red has the minimum frequency and violet has the maximum. So increases in this way. Then comes the IR, the microwave. Then this FM that we hear, that is same. Then AM. So this total thing is called as radio waves. So this radio wave is used for our communication. For the small radio waves are used in our means FM, and that radio we use listen, and the long radio waves, which since it has the longer wavelength, so it is used in the telecom industry. So this different ray have different application in our daily life. So this X-ray is used in detecting the bone fracture. This IR is used in spectroscopy. So this is a different kind of term. Spectroscopy is used to characterize and compound or different thing. Then we have the microwave. This visible is used for looking things. Then we have the ultraviolet rays. It also used in experiments. So in this way, there are various aspects of electromagnetic radiation, and each have different application. Now next, we do have a question here. So it tells that we have to calculate the wavelength and nanometer associated with a proton that is moving with a speed of 1.0 into 10 to the power 3. So do not look into this question and get confused that you told earlier that the speed of light is fixed, but it is changing. So it depends upon the question. So it is just the assumption of the question that is taken by the examiner. So it can be changed only if it is mentioned, but until it is not mentioned, it will be always 3 into 10 to the power 8 meter per second. So it is given here that the speed of the light is, so C is 1.0 into 10 to the power 3. Mass of the proton is given. So mass of proton is given. It is 1.67 into 10 to the power minus 27. Minus 27. What it is kg. And again the H is given. So H is 6.63 into 10 to the power minus 34 joule second. And what do we have to calculate? We have to calculate the wavelength. So for this question, we need the, so we have to calculate the wavelength. Okay. So for this question, we need a different concept. So I'm telling this question earlier because we will confront this concept in the later part, and then I will ask you to solve this question. Okay, you keep this question in your mind, and let's move to another slide. So it says that what is the energy required to break 1 mole of Cl2 bond, that is, and 1 Cl2 bond means in per mole, that is required to break the Cl2 bond, and we have to calculate that what amount of energy will be required to break one molecule. So it is asking for one molecule. So for this you have to be aware about the mole concept. Okay, so what is the energy required, that is to break 1 mole of bond? So it is given delta E is equals to, or simply we can write it as E, why to delta E. So E is equals to 242 kilojoule per mole. 242 kilojoule per mole. So it is the amount of energy that is required to break 1 mole of Cl2 bond. So how many atoms does 1 mole have, or molecule 1 mole have? So I have told it earlier. So it will be always 6.022 into 10 to the power 23 Cl2 molecules. So this much molecule will require this much of an amount of energy. So it says that 6.022 into 10 to the power 23 Cl2 molecules require 242 kilojoule mole of 242 kilojoule of energy. So one atom will require, so we will simply apply the unitary method here. That will be 242 into, so 1 by 6.022 into 10 to the power 23. And what do you have to, what the longest wavelength that is required to break a single CC bond? So this will be our answer. So whatever you calculate and get, so this will be our answer to dissociate one CL-Cl bond. Now next we will move to photoelectric effect. So what is photoelectric effect? So if you see the diagram here, so it is of a photoelectric effect. So let me explain this phenomena. What is this phenomena? So suppose we have a circuit here. So this is our circuit. We put up here a battery. So this is our battery here, and then we are turning on this circuit. The circuit is not complete because there is no wire in this middle part. So here a metal plate is kept here. So this metal surface can be anything. So generally we take cesium. So why do we take cesium? Because cesium has the lowest ionization potential, or we can take any other metal which have lower ionization potential. Because why are taking this cesium? So what is the relation between lower ionization potential and the light we are using? So less ionization potential means we will require less energy to abstract that electron. So we take that metal only which has the lowest ionization potential. So cesium is the most suitable candidate in that. So when we turn on the battery here, we turn on the circuit here, we do not see any deflection in the emitter. Why? Because the circuit is not complete. Now what we will do, we will incident a light that is of a certain frequency on this metal surface. And then what we will see, that emitter shows a deflection, some amount of deflection here. So what is the reason behind that? Einstein explained it, and many more scientists also explained it. So Einstein was the first to explain it. So how does it happen? He said that when the light is incident on this metal surface, this light is composed of photons. So photons are nothing but, so I'm not representing photons like this, means photons are not a part, this is not visible through naked eyes, but suppose I'm representing it using a circle, so for this time being. So what does happen in this phenomena? These photons do incident on this metal surface, and it's transferred kinetic energy to the electrons that are present on the surface of this metal or the cesium metal surface. Due to this kinetic energy, the electrons that are present here are released from this metal surface because they get the enough kinetic energy to break the to break the bond that they are included in and move towards this positive part, that is the cathode. And since this electron can move from here to here, the current is passed, and we see a small amount of deflection as the light incident on it happens. So this was the phenomena. So the question arises here that we have earlier studied that the light has a wave nature, it has a crest, it has a trough. Then we have studied it as a frequency, it has a wavelength and all those things. And in this phenomena, we consider light as a particle. So this was the contradiction that scientists in that time came across. So what are the key observations? So I'm going thoroughly again through it. So the key observations are: electrons are immediately when a light of certain frequencies strike on that metal surface. The second and the most important key point is that as we increase the intensity of the light of that sufficient frequency, means the frequency should be same, then the number of or the deflection of that thing increases, means more and more light intensity increase, more and more current is observed. Now the third and the most important thing is that as we increase the frequency of the electron, then on increasing the frequency of electron, this current means this kinetic energy of this electron also increases. So we have the 3 points. First of all, we see that as the frequency light incident on that metal surface, we see a deflection. As we increase the intensity, the number of emitted electron increases, and hence the current. And as we increase the frequency, the kinetic energy of the electron, means with which it is traveling. So what do I mean by kinetic energy? So here the electron is traveling from here to here. So it must have some velocity. So due to this velocity, it must have some kinetic energy. So this kinetic energy is increasing as we increase the frequency of this incident wavelength. So these are the key points. Now next, the Einstein proposed this photon theory to explain this phenomena. So what he said was that okay, we do have an energy associated with that photon, and it is nothing but E is equals to h nu, where nu is the frequency of light. We can also write here E is equals to h c by lambda, as nu is equals to c lambda. What is h here? So h is here the Planck's constant, and it is 6.63 into 10 to the power 34 joule second. Joule second. Sorry, 6.6 into 10 to the power 34 joule second. So this is our Planck's constant. Then next we have the frequency, that is nu, then we have the energy. So he explained it. Now next, what does happen? So we will see some of the key points that what is the frequency associated and how it is decided that which frequency should we take. So first of all, there is a particular frequency below which the photoelectric effect is not observed. Yes, that is true. So if you are applying a incident ray on it, and suppose you are keeping some frequency, so the frequency is different for different metal. Means this frequency is characteristic of the metal that we are using, and this frequency is different for different metal, and it is called as threshold frequency. So if you incident the light on a metal surface, no matter what is the intensity of the light, there will be no photoelectric effect until that frequency is equal to the threshold frequency of the metal surface. Now, next point we have. So if you want to calculate the kinetic energy of that particle, so how will calculate it? So it is simple. So this is the h nu. This is the incident light frequency. Incident light frequency minus the work function. So what is this work function? So this work function is nothing but the energy which is the minimum energy that is required to plug that electron, and where it is given by h nu naught. It is given by h nu naught, where nu naught is the threshold frequency. So if you have to calculate the kinetic energy of that photon, you simply have to subtract the energy of the electron that we are supplying with, photon that we are supplying with, minus the threshold energy, or the work function. And how it is calculated, work function? So it is nothing but h nu naught, where nu naught is the threshold frequency. So here we are given a question here. So it says that in a photoelectric effect experiment, the threshold wavelength of light is 380 nanometer. So it says that, so threshold wavelength is nothing but the minimum wavelength which will be required to plug the electron. So it is 380 nanometer. And it is said that if the wavelength of the incident light is 260 nanometer, so we have the incident, so I am representing it by lambda I. It is 260 nanometer. So first of all, we convert it into meter. So it will be 10 to the power minus 9 meter, and it will be also 10 to the power minus 9 meter. What is the maximum kinetic energy of the electron? So it is asking about the kinetic energy. So what is the formula for kinetic energy? We have seen it earlier. So it is nothing but the energy of the electron, that is h nu, minus the work function. So we are given here work function formula is, I am direct putting the work function formula, which is nu naught. So what is the formula for nu? It is c by lambda minus hc by lambda naught. So this hc is constant for both light. So I have told it earlier. So until and unless it is not mentioned that what is the value of c, we will take it as 3 into 10 to the power 8 meter second per second. So we will take this hc outside, and it will be 1 by lambda minus 1 by lambda naught. So you put this value here. So so here the incident wavelength is lambda I. So it will be lambda I. So 1 by lambda I minus 1 by lambda naught. So we will get your kinetic energy. Okay, you will get the kinetic energy of the electron. Now next we will move to hydrogen spectrum. So what is hydrogen spectrum? So students, when we apply light on anything, so whenever we apply light on anything, it absorbs that light, and electron uh, do get excited in the stationary state, means they move from the lower level to upper level. So if we supply energy, then electron goes from lower energy state to higher energy state. Now they do fall back also. So suppose electron goes from here and it falls back, so it limits energy. So we can have different type of transition in that case. So if we take n is equals to 1, so means each of this electron is falling on n is equals to 1. So we have the transition for n is equals to 1 to 2, n is equals to 2 to 1. Then we can have n is equals to 3 to n is equals to 1. Then we can have n is equals to 4 to n is equals to 1. So the series which we are getting here, so if for each of this you will get some amount of energy released in this through this process. So as this transition is made, some energy is released for each of this transition in the form of photons. And this photons have the frequency in the spectrum part of ultraviolet rays. So these rays which are released are ultraviolet rays. Now in the next series we do have the Balmer series. So we have different series. So if electrons are moving to n is equals to 1 from different shells, then we have the Lehman series. But if the electrons are moving to n is equals to 2, then we have the Balmer series. Then we have the Pascal series. Then we have the bracket and the P fund. So I'm writing it here. It is not mentioned here. It is bracket series. Then the P fund series. So in this way, we do get different series, and this series fall in the different classes of electromagnetic spectrum. The Lehman series fall in ultraviolet rays. Then we have the visible rays for Balmer series. Then we have the Pascal series for infrared. So as you can see from Lehman to Balmer to Pascal, we are moving from the we are moving towards the less frequency. So we are moving towards less frequency here. So this series are characterized through some formula, and this formula was given by Balmer. So this is an important formula. Many questions are asked in JEE each year from this section. So what does this formula is about? So it is about the wavelength of the light that is emitted. So you can see here that lights are emitted from during the transition, and the wavelength of each of the light, the inverse of wavelength of each of the light is given by RH 1 by n1 square minus 1 by n2 square, and this RH is called as the Rydberg constant. So it is written here, it is the Rydberg constant. What is this n1? So this n1 is the initial one from which the electron is falling, and n2 is the middle one, means the lower one to which the electron is falling to, means the n1 is the initial one and n2 is the final one. Then lambda is the wavelength, and the inverse of lambda is called as wave number. So this is another characteristic of light. So I'm not mentioned it earlier, so I'm mentioning it here. So it is nu inverse, which is 1 by lambda, and it is called as wave number. So do we have a question here? So what is this question about? So this question asks that the frequency of light emitted for the transition n is equals to 4 to n is equals to 2 is equal to the transition in the hydrogen to which of the following. So you will calculate the energy that is released, the frequency that is released during this different transition. So in the first slide, in the previous slide, we have seen that the value of the Rydberg constant is 1.09734 in 10 to the power 7 meter inverse. You should keep in mind this constant. So we can solve this question now. So what does this question say? That we are having a transition from n is equals to 4 to n is equals to 2. So this is the initial, and this is the final. So we have the formula 1 is equals to lambda RH 1 by n1 square minus 1 by n2 square. We know that 1 by lambda is represented as, so if you know the formula earlier, so if you remember the formula I mentioned earlier, the C is equals to nu lambda. So we have to calculate the frequency. So nu will be is equals to C by lambda. So if you put here the value, it will be C upon lambda. Now we know that R is equals to 1.0977977 into 10 to the power 7. What is the value of n1? It is 1 by 4. The initial is 1 by 4 square minus 1 by 2 square. If you calculate this value, you will get your frequency easily here. So this is the formula you can calculate. So you will calculate is n is equals to 4 and n is equals to 2. Then you will calculate for different numbers, means different transitions, and whichever will be equals to this n equal to 4 to n is equals to 2 will be the answer. Now next we will move to different atomic models. So due to this transition, so we have seen that we are having a transition. So this Balmer series was discovered first, so I have covered it first. So you will see the magic of this Balmer formula later on, when this atomic model will prove the value that was given. So it was in great accordance with that value. So what is this first? This is the model that we will study. So the students who are not aware about this JEE syllabus, I hope so you have seen the latest JEE syllabus which had been reduced, and the Rutherford model and the one more model, that is the pudding model, have been removed from our syllabus. So we have the only atomic model which you have to study is Bohr model, and also delta atomic theory, which is in the first chapter. So what does this Bohr model say? It says that electron can only revolve around the nucleus in fixed radius and the energy of each of this stationary state is fixed. And this path in which the electron is revolving, they are known as stationary state or the allowed energy states. So what does it mean? So electron cannot just simply revolve in any radius of any arbitrary radius, but it has to revolve around the photon in certain fixed radius. And also the energy is fixed, means energy cannot change easily without any incident light or until any light is incident on that shell or atoms. Now electron can do jump from one energy level to another energy level by absorbing energy or emitting energy. So if it's absorb energy, it goes to a higher energy level, and if it's emit energy, it goes to a lower energy level. Now on going from one energy level to another energy level, we do have emission of light, and the energy that is emitted during that, it is represented by the formula E is equals to h2, means the incident light which we are seeing will have the energy is equals to h nu. Now this is the interesting part of the Bohr model. He said that okay, the electron can revolve around the nucleus in certain orbit only, but he has said that in those orbit only in which its momentum, angular momentum especially, so it will be angular momentum, in which its angular momentum is multiple integral of h by 2 pi. So n can be here, n can be here, n is equals to 1, n can be 2, 3, 4 and so on. So this was an interesting fact about the Bohr's model. He said that electron can revolve around the nucleus in certain radius such that its angular momentum is equals to integral multiple of h by 2 pi or h cut. So h by 2 pi is also called as h cut. And n can be any number, any whole number, that is 1, 2, 3 except 0. So we will start from, so you can say it as natural number. So n can be any natural number. Now we have the energy of a stationary state. So what is the energy of each of the stationary state? So it is simply minus RH 1 by n square, and it is for hydrogen atom. So student, do not get confused with it. So you will not use it for any other compound, so any other atom like lithium atom or helium atom. So it is only for hydrogen atom. And what does this formula said? It is 1 by n square and RH. So this is the magic of the Balmer formula. So Bohr do calculated this equation using this many modern techniques, but Balmer calculated it earlier, and this RH value was in close proximity with this value which Balmer has calculated. So this was the magic of the Balmer formula. Now, if we are considering another other hydrogen-like species like helium plus or lithium 2 plus, then the radius of the nth orbit is given by 52.9 into n square by z. So this z is here the atomic number of the atom that we are taking. So for helium, hydrogen, it is 2. For lithium, it is 3. So this number will vary like this. Now next we have the energy of the nth orbit. So we have seen that the energy of the nth orbit is minus 13.6 into 1 by n square electron volt for hydrogen atom. But if we have to consider for every atom, means every hydrogen like atom, then we do have the z square. So why this z is appearing here? So it is happening because we do have the photon that is present here. So the number of photon is increasing as we are increasing the atomic number. So for different atoms which are hydrogen like, we do have to increase the charge upon it. So due to increase in charge, we have to introduce this z square. And so do we get the final formula for all of this. So you can use for hydrogen also. So for hydrogen it will be 1, for helium it will be 2, for the lithium it will be 3. And this is the formula. So it is in joule. So this is the formula for calculating in joule, and it is for electron volt. Next we have the velocity of the electron. So it has a formula of 2.18 into 10 to the power 8 into z by n. So z again here it is the atomic number, and n is the nth shell that we are considering for. So this is in centimeter per second, and this n can be any value that is natural number 1, 2, 3, 4. So in this way we can calculate the velocity of the electron. So why this Bohr model was removed? So later on this Bohr model was not recognized. Means it was recognized due to its very exceptional results like the radius, the velocity, the energy, but it has some limitation. So if you consider the limitations of the Bohr model, the first one was it was unable to explain the spectra of atom with more than one electron. So I have told you earlier that you are using it for helium 2 plus and helium 3 plus, but you are not using it for multi-electron system, like if we have only helium or only lithium, or we have a greater atomic number like calcium and any other. So why it was so? So during this calculation of Bohr model, we are only considering the electrostatic interaction between the electron and the proton. But as we move to the higher atomic number, then we do have the repulsion between the electrons itself, and due to this mutual repulsion, the net force on the electron is changed. But in Bohr model, no such consideration of interaction between the electron was considered, due to which the Bohr model was failed to explain this multi-electron system. Now next, it could not explain the fine spectral line of observed in the hydrogen atom. So if you see the hydrogen atom spectral lines, it was again, so you do not have a picture here. So if you see it more closely, then these spectral lines are again split into some small transitions. So suppose the transition we get here it is. So what is the transition I am telling about you here? So the transition we got during Balmer series, for different series, we saw it as one line from, suppose from n is equals to 4 to n is equals to 1 for Balmer series. We got one line. But if it was observed more closely, then it was seen that this line was not a singular line, but a collection of many lines. Means it was splitted into many lines again. And Bohr model could not explain why from the same shell we are having the transition, and as the energy for one shell is fixed, then why are we getting this multiple types of spectral lines in this for hydrogen atom. Now further it could not explain the JEE-Main effect and the star effect. So what is JEE-Main effect? So JEE-Main effect is nothing but this splitting of this spectral line in presence of magnetic field. So this is a higher modern chemistry or modern physics, you can say. magnetic effect. So this was later explained by quantum mechanics, but Bohr model could not explain it, and it is this Stark effect is it is due to electric effect or the electric field, we can say. So what does it mean? So if you apply magnetic field on this rays that we are getting due to transition, they do a split again, or if we apply electric field also, they do split. So this Bohr model could not explain the splitting of light in the presence of magnetic field or electric field. One more point I have not mentioned here because we have not seen the Heisenberg uncertainty principle. So Heisenberg, so I'm putting up just a point here, I'm not explaining it here. So when you will study the Heisenberg uncertainty principle, you will come to know that why the Bohr model was a failure. So it was the most you can say the major drawback of the Bohr atomic model. So Bohr says that. So I'm just giving an overview brief of it. So Bohr says that if electrons are revolving in the orbit, then the energy and the position was fixed. Means he decided the energy and he can tell the position of the particle both at the same time simultaneously. But Heisenberg uncertainty principle was just opposite of that. So you will see what is Heisenberg uncertainty principle, and this was the most major drawback of the Bohr's atomic model. Now next, we will move to another question here. So this question is very simple. So which of the following is the energy of a possible excited state of hydrogen? So what is the formula for hydrogen? So it is given in electron volt. So the formula for hydrogen is, for nth energy state, it is minus 13.6 Z square by n square. So this is the formula for this thing. Now, if we put the value of En here, and we know that the value of Z is 1 for hydrogen atom, that is n square. The energy, and if we put the energy each and every energy one by one, then you will get some value of n. And it is asked that which of the energy is possible. So in which answer you will get the perfect square root, then that will be the answer of the given question. So you try it once. If you have any problem, then you can put a query in the router site, which is where your question will be solved easily. Now, the next question we have here, it is the radius of the second Bohr orbit of the hydrogen atom. So what we have to do, we have to calculate the radius of the second Bohr orbit. So we know the formula. So if you go to the previous slide, so we have the formula of calculating the Bohr radius, that is 52.9 into n square by z. (52.9) into n square by z. It is in picometer. So the means the unit is not mentioned in here. So if you want, you can calculate it in angstrom. So I'm leaving it as an exercise to you. So I'm not solving the question here. So if you go and solve it once again, you will get a grasp of the you have to get a grasp of the concept for that, so that you can get the concept clear. So I'm not solving it, I'm just putting it here. So just solve it for picometer and then again convert it into angstrom to get your answer. So the next and the most magical thing of this slide, you can say, is the de Broglie principle. So this principle is nothing, is more a hypothesis than a principle. So what is a hypothesis? So hypothesis is something which is not experimentally verified when it was written, but it was thought of, or you can say calculated or something, but it was not experimentally verified. It was just written by some scientist. Here it was given by de Broglie. Let me tell you an interesting thing that D. Broglie was not an physicist or a chemist. He was an historian, but still he gave that hypothesis, and this hypothesis came to be magical in the coming centuries. So, what does this hypothesis says? So, this hypothesis says that we have seen that light have a particle nature. Then we have seen that okay, light have a wave nature. So there were two phenomena, or more than two phenomena, you can say. So the particle nature was explained. I was explaining the photoelectric effect and the Compton effect. Means you will study the Compton effect later on. While the wave nature has explained the interference and refraction. So you must have studied in physics about those phenomena. So different phenomena was explained by different of nature of the light. So later on, it was concluded that okay, light have both wave nature and the particle nature. So to explain that wave nature and the particle nature, de Broglie was considered as the periphery, means where both this particle nature and the wave nature met each other. So he gave such formula where the periphery of the wave nature and particle nature exist. The formula is such that lambda is equals to h by p, where lambda is the wavelength, h is the Planck's constant, and p is the momentum of the particle. So momentum is equals to, so p is equals to mv. So you can again write the formula more expanding it as it lambda is equals to h by mv. So it was written by keeping in mind that wave has both a particle wave nature and a particle nature. So before moving to the question, let me give you the derivation of that. So let me tell you a more complicated thing about it. So this, Miss, I have said earlier also that this formula is not derived or not means was not experimentally verified. It was just a hypothesis. But later on, when it was experimentally verified, it came out that this formula is true, and it is very verified for every means particle, you can say elementary particle in entities. And further, the most interesting thing which I mentioned earlier also, that de Broglie was not a chemist, not a physicist, not related to science. Science also, he was a historian. Yet he gave that formula. If you want, I can give you a derivation, a short derivation. It is a very short derivation. So we know that Einstein mass and energy relation, which is E is equals to mc square. And also, we know the Einstein hypothesis of this photon, that is delta is equals to h nu, or you can say energy of any photon is equals to h nu. Now, if you this means equate both these equations, so you will get it as mc square. I am replacing it c by v, so velocity, because energy can be related to any speed, means it can be light speed also, it can be LA speed also. So light we generally use c, so I am replacing it by v. So mv is equals square is equals to h nu. So what do we have later? So if you want, we can write it as mv. So v is equals to speed of any wavelength is equals to c is equals to nu lambda. So it will be nu lambda. This nu and nu will be cut off. So lambda is equals to h by mv. So this is how you get your de Broglie hypothesis or de Broglie equation, which gives about the which deals about both the particle and the wave nature of a elementary particle like protons or electrons, and its wavelength is given by h by mv. So he said that every particle that do exist in nature, both means it is not only associated to a microscopic particle like a electron or a proton, it is also associated to a macroscopic particle like a table or a chair you see around, or a moving car. It also has a wavelength. But the main problem here is that its mass is such large, so it has a larger mass, due to which that wavelength becomes so small and it becomes insignificant for that as compared to the size of that car. Due to this reason, this lambda is only significant for the elementary entities like electron, proton, or neutron. Next upon, we move to a question here. So it says that the energy of an electron is increased 4 times. So what? So it says that suppose we have an energy that is Ke. So we call it as kinetic energy initial. So it is increased by 4 times. Means the initial energy is means the final energy is 4 times the initial energy. Then what we have to find? We have to find the wavelength of the de Broglie that will be associated with it become. So let us suppose that the initial wavelength is lambda I and it goes to lambda f. So if we calculate here, so how we will calculate? So we know that kinetic energy is equals to half mv square. So mass will be same because we are considering an electron. An electron has the same mass. So I'm writing it here by the subscript as mevi square. Then we have half me vf square. This me and this me will be cancelled. This half and this half will be cancelled here. So we have 4vi square by vf square. Now we know that lambda is equals to h by mv. So if we want, so if we can put the value of v from here. So what do we get? We get it as h by 4 lambda, h by m lambda. So we get it as vi square. So I'm replacing it by h by mv. Sorry, h by m lambda. So here it will be also h by m lambda, and it is square here. So if we take the square root on both sides, so it will be 2h m lambda is equals to h by lambda. Now mass is same. So I'm yes, here the wavelength will be different. H is same. The difference it is about that wavelength, which is f, and I means lambda I and lambda f. So what is the final result we will get? So lambda final will be 2 times the initial wavelength. Sorry, the means the final wavelength will be half of the initial wavelength. So this is the relation we got. So this one is the correct answer. Okay, so this was for today's class. So one question we have seen earlier in the previous slide, and I told it earlier that we will solve it at the end of the class. So what was that question about? So this was the question. So it says that you have to calculate the wavelength associated with a proton that is moving at 1.0 into 10 to the power 3 meter per second, and mass is given and the h is given. So this is the speed, and we have to calculate the lambda. So what do we need for lambda here? We need h upon mv. So h is constant and it is given here. It is 6.63 into 10 to the power minus 34 joule second. And we do have the mass of proton. It is 1.67 10 to the power minus 27. So we can write here at 6.63 into 10 to the power minus 34. Okay. And again, we can put the mass value here from here, and then we can calculate the wavelength associated with it. If you get the answer, you will get in meter. Then convert that meter into meter into nanometer, and you will get your answer. The next example is we have to calculate it for. Oh, we have done this. So this was our class. So once again, if you do have a query, you can ask now, or you can put it in the query section of the router. If you want, you can also contact me through my mail. So it is Shashank at the rate robustresults.com, or you can put it in the query section of the router. So thank you for your time. So that was for today's lecture. So in the next lecture, we will be moving to the next part of the atomic structure, in which we will be discussing about the quantum mechanics modern mole. Okay, thank you.